All right. Ordinary comparison tests. It's known as the OCT. Suppose that for the sum of n equals 1 to infinity of an and the sum of n equals 1 to infinity of bn are series with positive terms. If the sum of n equals 1 to infinity of bn is convergent and an is less than bn for all n, then the sum is n equals 1 to infinity of an is also convergent. Now, if b is divergent and a is greater than bn for all of n, then an is also divergent. Now, what this doesn't account for is if b is convergent and a is greater. We don't know. Or if b is divergent and a is less than. We don't know. Okay? So, these are just some specific situations. All right, so using the OCT most of the time, we'll either use P series or geometric series for AN. All right, so we are going to make a we're going to make an AN value. We're going to be given that this right here is the sum of BN. Yes. So we're going to make an AN value. And again, the AN value we're going to make is either going to be a geometric series or a P series. And it really just depends on what we have. For example, if we're looking at this one, since we have n in both exponent, both numerator and denominator, it'll probably be easiest to make this a geometric series. All right. So what's a geometric series that's close to this one? Yeah. So we can say the AN would be the sum of 2 over 3 to the n power.
What, AN?
Yeah. AN. It is AN, right? In the notes. This is BN. We're going to make an AN value. All right. Now the quick question is AN convergent or divergent? It is convergent, yeah. So the sum as n goes from 1 to infinity of 2 over 3 to the n is convergent. All right. Because the absolute value of r is less than 1. Right. Now, is an less than bn or is bn less than an?
Yeah, that's great.
Yeah, so in this case, see here? In this case, since 2n over 1 plus 3n is less than 2/3 to the n power, right? What does that tell us?
Nothing. Oh, that it's divergent. No, nothing. It tells us something.
No, we had it.
Yeah, it's convergent. Oh, did I do it? Sorry. I can't read this lady's handwriting. So I know, as bad as my handwriting is, I couldn't read hers. I had it backwards. Yeah.
So then.
Yeah. That does make more sense. Yeah.
Oh, she can.
No, it's still convergent. It follows that first rule. If if BN's convergent, then AN must also be convergent.
Wait, is A and B like switched around in the rule above? Because it says, is BN in like the rules that are written above AN in this situation? Like, did we switch the way?
I'd switch them around. I'd switch them back.
Oh,
So yeah. So in this case, this is AN. AN is less than BN. Okay. So the sum as n goes from 1 to infinity of 2 to the n over 1 plus 3 to the n must also converge.
I have a question.
Yes.
How do you choose if it's A or if it's B?
I think what we're trying to do is we are trying to make the initial value we have as AN, and we're picking a BN.
Oh.
So here, if we make this AN, we need to pick a BN that's close to this. Now, to keep it simple, what's an easy BN?
5 over.
1 over n to the 1/3 power? That's a P series, right? So compare this to be as n goes from 1 to infinity of 1 over n to the 1/3 power. In this case, AN would be less than BN everywhere, right? Because BN would be 5 times AN. So AN would be greater. AN would be greater than BN. All right? Because AN would be 5 times BN. I had that backwards again. Now, what do we know about P series and convergence and divergence? In order to converge a P series, the exponent must be what? Greater than 1. In this case, the sum of n goes from 1 to infinity of 1 over n to the 1/3 does what? Diverges. And since AN, in this case, is greater than BN, 5 over n to the 1/3 is greater than 1 over n to the 1/3. The sum as n goes to infinity, n goes to 1 to infinity, 5 over n to the 1/3 power must also diverge.
Did that? No, right?
Yeah. Again, the idea is we're trying to pick some easy functions, okay, that we know either converges or diverges. In this case, this is AN. What's my BN going to be?
One over and then the n. What would it be?
that's 3N?
You can make it, since 1 to anything is 1, we can make it n. So this would make it what kind of series? Geometric. Now, in this case, will an always be bigger than or less than bn? Well, in this case, less than or equal to, because if n is 1, then it would equal it. Okay, so in this case, an will always be less than or equal to bn. Now, does bn converge or diverge? The sum as 1 goes from 1 to infinity of 1 over 3. R is less than 1. So since the absolute value of R is less than 1, it converges. All right, which means sum as n goes from 1 to infinity of 1 over n times 3 to the n must also converge.
Why didn't you really look at the end, the A and one going to the end? Like, why didn't you include that in your A?
How would I include it?
And
What? 1 over n times 1/3 n?
yeah. Or 1 over 3 to n.
Well, the idea is we just wanted to make another function that's easy, and we know it'd be less than or greater than everywhere than the other function. In this case, 1 over 3 to the n power would always be less than or equal to
Yeah.
1 over n times 3 to the n. And
Just one, yeah.
oh, just 1 over n? That wouldn't. What function is that? What kind of function is that? And would that converge or diverge? Oh, but 1 over n compared to the other one, would there be places where it would be less than that everywhere?
I don't just.
No. It wouldn't work because it would be greater than 1 over n would be greater than 1 over n times 3 to the n power. Yeah.
So we just wouldn't have any answer.
Yeah, you wouldn't have an answer there.
Yeah. Because it wouldn't apply to 1 to 2.
Yeah.
Yes, but it's,
So
I'm still back.
For number 11, how do we know that it's what is it, less than or greater?
It's less than. 1 over 3 to the n is less than 1 over n times 3 because you're
Right.
multiplying by n, so your denominator will be multiplied by another value. And again, if your denominator gets bigger, your function gets smaller. All right, that is it for the OCT. Next for the LCT. Sometimes the OCT is not very useful, as in this case, 1 over 2 to the power of n minus 1. All terms are actually larger than the terms of the sequence of 1 over 2 to the n. We suspect will converge because the two are so similar. All right, we must use a different test. So, suppose the sums as n goes to 1 to infinity of a and bn are series of positive terms. If the limit as n goes to infinity of an over bn is equal to a constant, such that the constant is positive, then either both series converges or diverges. Well, we would know if one converges or diverges. Yep. So the issue comes with this one right. This one right here. If we try to use the OCT for this, is 1 over 2 to the n less than or greater than 1 over 2 to the n minus 1? Remember, when is it greater? Is when your denominator is smaller, right? So 1 over 2 to the n would be greater than 1 over 2 to the n minus 1. So in this case, your b would be less, sorry, your a would be less than b, right? So a is less than b. All right. Now, does 1 over 2 to the power of n converge or diverge?
Converge.
Converge. So what's the problem here? So because a to the n is greater than, sorry, a to the n is not greater, it's less than. I'm in trouble why there's an issue here. Okay, so a to the n is greater than b to the n. Oh, but yeah, so a to the n is greater than b to the n, but b to the n converges. It doesn't diverge. So it doesn't meet up with the with both aspects. So basically, if you think of it as this has to meet two parts. Part one, either A is less than B or A is greater than B. Now, if A is less than B, then AN must also converge. If AN is greater than B, then it must also diverge. But it has to meet these two parts. Okay, it has to meet part one, part two, part one, part two. In this case, we met part one of the first statement, but part two of the second statement. That was the issue.
Wait, so is Bn the like?
Bn was the 1 over 2 to the power of n. So 1 over 2 to the power of n, it converges, but it happens to be an is greater than bn. So that doesn't help us that it converges. Okay. So what happens when we get in a situation where this isn't useful? Well, we have this other test. So let's look at this other test. All right, let's see what happens. Let's go ahead and try this. What's the limit as... Okay, n goes to infinity of an, which is 1 over 2 to the power of n minus 1, of 1 over 2 to the power of n. Now, we can rewrite this, right? If you do your keep, change, flip, what are we going to end up with? So 2 to the power of n, right? As n goes to infinity, right?
What are we doing? What's this trying to find?
Trying to find if this reaches a constant or not. Okay? So let's y clear fraction to the power of x over to the power of x minus 1. So as I'm going to infinity, is it flattening out? Is it reaching to a constant? Yeah, it is. It is getting closer and closer to 0. Okay. So yes, this is reaching a constant.
We need it.
Yeah, you will need calculus. Right. So in this case, it is reaching a constant. Now this means both series either converge or diverge. What do we know about 1 over 2 to the power of n? It converges, which means 1 over 2 to the power of n minus 1 must also converge. So basically, we can use this in any case. If one converges, then the other one must converge. If one diverges, the other one must diverge, as long as the limit is n goes to infinity of an over bn goes to a constant. All right. So
All right.
Taco Bell, it's early.
Those are really.
Oh wait, I forgot they have breakfast because it's so terrible.
That, yeah, no.
I like how that's on the recording now. All right, every year they're going to hear really Taco Bell.
What?
Every year now they're going to hear really Taco Bell.
Basically, it's all-
I'm recording these videos and we'll use them.
Oh. I like. Should have.
So, what are we going to do with 2 to the power, or 2 over n cubed plus 4? All right. What are we going to compare this to? Wouldn't it be easier 1 over n to the third?
It's loud.
That is true, but does it have to? Doesn't really matter, does it? I mean, that's fine.
Yeah.
But it is easy because we do know 1 over n to the third would be a p series if it's 1. And that does what? I don't think it is. I think it needs to have just 1 over it. Yeah.
We'll change one thing about it with mod. Like we can't subtract 4 from the bottom and
Why not?
well, because they're like moving opposite directions, so that'd be it could. How to explain.
We're not comparing greater than or less than in this case. So in this case, we're going to compare this to the sum as n goes to 1 to infinity of just 1 over n to the third, because that's a really easy what? P series. Now, does this converge or diverge? This converges because the exponent is greater than 1. So we do know that this converges, all right, because the exponent p, in this case, equals 3 is greater than 1. So we're going to take the limit as n goes to infinity of the first value, 2 over n cubed plus 4, divided by 1 over n cubed, all right, which gives me the limit as n goes to infinity of 2n cubed over n cubed plus 4. Now, what's going to happen as this goes to infinity? Going to approach 2, which means it's a constant. So since 0 is less than 2, which is less than infinity, so both
Right.
series behave the same way.
Right.
Therefore, sum is n equals 1 to infinity of 2 over n cubed plus 4 converges.
Okay. Oh yeah. Basically all.
Let's look at this one.
We're gonna move all that extra time out. Then I'm not positive.
We move on. So let's look at this one. Number 13. What function do we want to compare this to? Now, keep in mind, when we do the whole keep, change, flip, what kind of exponents do I want up top? What exponent do I want on top and the bottom? What would give me a constant?
Same.
The same. So what can I multiply the numerator by to get the same exponent? Same leading exponent? N to the third, right? So I should probably compare this to the sum as n goes to, or n equals 1 to infinity, of 1 over n cubed.
Which also
If we just did number 12, this does converge. So this converges because p is equal to 3, which is greater than 1. So we take the limit as n goes to infinity of 4 plus n over n to the fourth plus n squared plus 1 divided by 1 over n cubed. That gives me the limit. N goes to infinity of 4n cubed plus n to the fourth over n to the fourth plus n squared plus 1, which is 1. Because we know how this works.
It's a word.
Yep. So since 0 is less than 1, which is less than infinity, the series behaves the same way. Therefore, the sum is n equals 1 to infinity of 4 plus n over n to the fourth plus n squared plus 1 also converges. To be honest, this is probably the easiest way I've seen this be done. I like this way.
I have a question.
Okay.
Can we take can we, for our second function comparison, can we do any function?
Function, really, yeah. Because we're just going to take the limit as one goes over the other of my initial function divided by my second function, my new function. It doesn't apply to OCT. It does have to meet 2 criteria.
Criteria?
Where the first one, if you're thinking it diverges, if you're thinking it diverges, then a to the n must be greater than b to the n.
Okay.
If you're thinking it converges, then a to the n must be less than b to the n. In this case, we don't know. Yeah. So we pick an easy function. Now again, if I have a function where n is my base and I have an exponent, I'm going to be using a p-series. Okay. So I'm using p-series. And I want to have the same exponent up top. So that's why I chose 1 over n cubed, because that would give me the same exponent on the top and bottom. But number 14 is a bit different, isn't it? 14, n is an exponent. And so what series am I probably going to be using? Geometric. So in this case, I probably want to have the same function on the top and the bottom, right? Okay. Now in this case, would I want to use the LCT? No, I could probably use the OCT. Yeah, in this case, I would want to use the OCT because I can easily say that any geometric function I create would be less than or greater than this one, right? So, in fact, I can easily say my A of n is going to be greater than my B of n because what's being added is being added to the numerator this time. So yeah, so that will always make my other geometric function, my B of n, less than A of n. So, what we'll do, let's say that this is A of n. My B of n is the sum as n goes to 1 to infinity of 3 over 2 to the n. Now, does this converge or diverge? This diverges. This diverges because absolute value of r is what? Greater than or equal to 1. All right? And since a to the n is a to the n greater than b to the n for all n, all right? So 4 plus 3 to the power of n over 2 to the power of n will always be greater than 3 to the power of n over 2 to the power of n, which we know diverges. The sum as n goes from 1 to infinity of 4 plus 3 to the power of n. Hey. Over 2 to the power of n must also diverge.
So, the LCT thing only works for like similar platforms. Like you can't just take two.
If I can't think of a function, like for example, if I can't think of a function that I want to do, would I want to do really a good limit comparison test for this? How would you simplify that? It's honestly, which one's easier to do is always my first approach. Okay. OCT is obviously very easy to do if you can you can think of a function that will either always be less than or greater than your given function. But if I can't, because I have functions like, especially like 13, there's no way I can think of a function that will always be less than or greater than this one. All right. So here I would do the limit comparison test. Yeah.
We were able to like take out the n because both the top and the bottom were to the power of n. But on number 11, only the bottom number was to the power of n.
Was it a 1?
Yeah.
Number 11? Wait, not number 11. Wait, number 11. Yeah. 1 to the n is 1. So you can always take out n from 1. Any 1 to any power is always 1. So, yeah.
It's any number.
Any other number, then we couldn't do that now. Yeah.
What if it was a different number?
Then I couldn't have done that.
Oh, yeah. Then we just wouldn't have done that one.
Well, we would not have. All right. So in this case, can I do an OCT? Can you think of a function that will always be less than or always greater than this function? No. But is it easy to just get your numerator to be the same as your denominator? What would I need to multiply your numerator to be the same as the denominator? Yeah. So I'm going to say 1 over n. All right. Now 1 over n is a common harmonic series. Is the harmonic series, and the harmonic series does what? Diverges. So we're going to compare to compare to the sum of 1 over n, which we know diverges. All right. So since we know this diverges, we are going to take the limit as n goes to infinity of n to the 4th plus 1 over n to the 5th plus 2 divided by 1 over n, which gives you the limit as n goes to infinity of n to the 5th plus n over n to the 5th plus 2, which gives you 1. So since 0 is less than 1, which is less than infinity, these series behave the same way. Therefore, the sum of n goes to 1 to infinity of n to the 4th plus 1 over n to the 5th plus 2 also diverges.
Mm-hmm.
All right. 16. Okay.
Your handwriting is getting. I just don't understand the limit. Like,
What do you mean the division? Keep, change, flip?
today, right? Oh wow, I'll
It's been a while. Even I know it's been, what, 2 years since you've done keep, change, flip. I don't know how much you do that in pre-algebra, but probably not a lot. Or pre-calc, sorry. Pre-algebra.
Okay, I bet this one.
So for this one, can I think of a function similar to this one that either converges or diverges that will always be less than or always greater than this one? No. So I'm going to do the LCT. Now, what is the actual exponent, leading exponent of your denominator?
I mean, 1/2. No.
3 halves, right? That is your actual leading exponent, 3/2. Okay? So I need to make my numerator also 3/2, which means I'm going to compare to what?
So, is that compare, is that two?
Yeah, sorry.
It's okay. Oh, okay, yeah.
Compare to the sum of 1 over n to the 1/2. Because that would give me 3/2 in the numerator if I do your keep, change, flip, right? What does this function converge or diverge? Diverges because p is equal to 1/2, which is less than 1. If it's greater than 1, it converges. Less than 1 diverges. So we take the limit as n goes to infinity of n over, again, the cube root, or square root of n cubed plus n plus 1 divided by 1 over n to the 1/2. This gives you the limit as n goes to infinity of n to the 3/2 over the square root of n cubed plus n plus 1, which in this case would equal 1. Reason being is because you can ignore anything but the highest degree. Anything but the highest degree will always go to what? Always go to 0. So, both series behave the same way.
Like 0.
Oh, thank you. I forgot that. 0 less than 1 less than infinity. All right. So both series behave the same way. Therefore, the sum as n equals 1 to infinity of n over the square root of n cubed plus n plus 1 diverges. 2. And this is where we're going to stop today.
No more.